Hi everyone. Today I'm going to present TASO, which optimizes deep learning computation with automatic generation of graph substitutions. And this is a joint work with colleagues from Stanford University. Let me begin by explaining existing rule-based optimization for deep learning. So every deep learning model is described by a computation graph. So each node in the computation graph is some tensor algebra operations, such as convolution, matrix multiplication, or ReLU, which is a very simple nonlinear activation function. And edges in the computation graph indicates data dependencies between different operators. And existing deep learning systems generally use a rule-based optimizer, which includes a number of manually designed rules to optimize an input computation graph. So one such rule could be you can fuse a convolution and the following ReLU into a single fused convolution plus ReLU operator. And we can iteratively apply these manually designed rules on the input graph to obtain an optimized computation graph. And each rule is implemented in source code. So the right figure shows the TensorFlow code for implementing convolution plus ReLU fusion rule. And overall, TensorFlow includes around 200 different rules written in 53,000 lines of code. And we think there are a few limitations with existing rule-based optimizations. First is robustness, because these rules are designed based on domain experts' heuristics on common model and hardware. We found that they do not necessarily generalize to all model and hardware combinations. And as a result, you can find people on GitHub or Stack Overflow complaining that if I turn on TensorFlow's graph optimizer, my performance is slower instead of faster. And second limitation is scalability, because this new operator and new graph structures all require new optimizations. And it is very expensive to support these new optimizations in rule-based approach. For example, today TensorFlow involves around 4,000 lines of code to optimize convolution. And you can imagine a similar amount of code effort to fully optimize a new operator. And the third limitation is performance, because our human heuristics may miss some subtle optimizations for very specific model and hardware combinations. So let me show you one motivating example. So the left figure shows the optimized computation graph of ResNet modular by existing rule-based optimizer. And it turns out we can further optimize it as follows. So first, we can enlarge this 1x1 convolution kernel to a 3x3 convolution kernel by just setting the extra parameters to be 0, so that mathematically you still compute the same thing. However, this is a performance decreasing step because you just introduce additional computation to your model. But this allows us to do further optimizations because you can fuse the two convolutions now, as they have the same kernel size, to a single convolution. And in addition, you can also fuse the convolution and the following addition to a single convolution by changing the parameters of the convolution. And finally, you can also fuse the convolution and the following ReLU. And it turns out that the final graph is 30% faster on V100 GPU, but 10% slower on K80 GPU, which means this is not a generic optimization. It only works for very specific model and hardware combinations. So it turns out that designing deep learning graph optimizations is very challenging because it depends on the operators you use, the graph architectures, and also the hardware backends. And different combination of the three components will result in different graph optimizations being applied. And this makes it infeasible to manually design graph optimizations for every single combination of the three components. So one research question here is how should we address the high complexity of designing deep learning graph optimizations? And our approach to tackle this problem is called TASO, which is a tensor algebra super optimizer. The key idea of TASO is to replace today's manually designed graph optimization with automated generation and verification of graph substitutions for deep learning. So this replacement brings two benefits. First, TASO requires significantly less engineering effort. For example, TensorFlow currently requires around 53,000 lines of code for manual optimizations. And in TASO, we only need 1.4 thousand lines of code to specify these optimizations. And second, this will result in better performance because TASO can automatically generate novel substitution optimizations that are currently missing in existing rule-based optimizer. And as a result, we can outperform existing optimizer by up to 2.8 times. And every subgraph substitution indicates mathematical equivalence between two subgraphs. So for example, this figure shows one graph substitution. It says if you do convolution on the same input but different weights, that is equivalent to first concatenating the weights, do the convolution, and finally splitting the output. And in order to automatically generate these graph substitutions, TASO takes as input a list of operator specifications that defines the available operators supported on your hardware backend, as well as the definition of these operators. And TASO will automatically generate candidate substitutions using available operators as basic building blocks. And these generated substitutions are sent to a verifier to formally verify the correctness of these substitutions. And the verified substitution can be used to optimize an input computation graph. So for an arbitrary input computation graph, TASO considers how to apply the verified substitution on the input computation graph. And this will give you a search space of potential computation graphs that are all mathematically equivalent to the input graph, but may have very different runtime performance. And we use a search-based graph optimizer to explore the search space, and we return an optimized computation graph. So there are two key challenges in TASO's approach. First, how to generate these potential substitutions, and second, how can you verify the correctness of these substitutions? And we use graph fingerprints to generate potential substitutions. And we use operator specifications plus a theorem prover to formally verify the correctness. And the TASO graph substitution generator will first enumerate all possible subgraphs up to a fixed size using available operators as basic building blocks. And in our evaluation, we enumerate all graphs with up to 4 operators, and this gives us 66 million different graphs. And because every substitution is just equivalence relation between two subgraphs, so one straightforward way is to compare the equivalence between every graph pairs. However, this requires n-square comparisons and Ohm's scale. So the fingerprinting techniques will compute the output fingerprint of each computation graph using the same randomized input. So the output of each computation graph becomes its fingerprint. So fingerprints provide a very nice property, which is if two computation graphs are not equivalent, then they have different fingerprints. If two computation graphs generate different fingerprints, they cannot be equivalent because they disagree on at least one data point. And as a result, we only have to consider pairs of graphs with identical fingerprints, and each such pair becomes one candidate substitution. And in our evaluation, TASO generates around 29,000 different substitutions by enumerating graphs with up to 4 operators. And 743 substitutions remain after applying a sequence of pruning techniques to eliminate redundant substitutions. So the detail of the pruning techniques are available in our paper. So once we have generated these candidate substitutions, our next task is to verify their correctness on arbitrary inputs. So the TASO verifier also takes as input a list of operator specifications that describes the mathematical properties of the operator. So for example, we know convolution is distributive over concatenation. And every property is written in first-order logic. For this example, we know for arbitrary x, w1, w2, if you do convolution over the concatenation, that is equivalent to distribute the convolution into the concatenation. And in order to verify the correctness of a substitution on arbitrary input, we can also translate this substitution into first-order logic by looking for a counterexample. If the two graphs are not equivalent, there must exist at least one counterexample such that the two graphs gives different outputs. And we can feed this query along with our list of operator specifications to a theorem prover. And if the theorem prover returns unset, meaning it can prove that there won't be such a counterexample, then we prove that this substitution is actually correct. And we have designed 43 different operator properties. And in terms of the generation and verification time, so TASO can generate all 743 substitutions in 5 minutes and can verify them against 43 operator properties in 10 minutes. And one interesting observation is that it turns out all generated substitutions are correct and can be formally verified by our verifier. And this also means that the fingerprinting is very efficient in discovering useful graph substitutions. And supporting a new operator requires a few hours of human efforts to discover its property. And again, we require significantly less engineering efforts to describe these graph optimizations. And once we have verified these substitutions, our next task is to apply this verified substitution to improve a computation graph. And we use a search-based graph optimizer adopted from our previous work, MetaFlow. And the key component of the optimizer is a cost model that can accurately estimate the runtime cost of a computation graph. So the cost model is based on the summation of individual operators' cost. And we can measure the cost of each individual operator directly on hardware. And we use a cost-based backtracking search algorithm to backtrack local optimal solution and allow us to explore more candidate computation graphs. And in our evaluation, optimizing a DN model from scratch takes less than 10 minutes. And note that for every deep learning model, you only have to optimize it once on your hardware. So we think this is reasonable. And this figure shows the end-to-end inference performance between TASO and existing graph optimizer on V100 GPU using cuDN library. That's the CUDA library for deep learning. And each bar shows the inference performance, and so the lower the better. And TASO can achieve competitive performance on standard model by only using automatically generated optimizations. And this means that TASO can automatically discover performance-critical optimizations on standard models. And the more interesting results for the new emerging models. So TASO can achieve larger speedups on new emerging models. So you may wonder why this is the case. So we have digged into these new emerging models, and we found that they have some new operators and new graph structures that haven't received full optimizations in existing rule-based optimization approach. And because TASO can automatically generate optimizations for them, we can achieve larger speedups on these new emerging models. And we have also evaluated our approach on the TVM backend, and we observed similar speedups. So more detail of this evaluation in our paper. And next, we would like to analyze which substitutions are useful to optimize our model. So this figure shows the heat map of useful substitutions. So each column shows one substitution, and each row shows one deep learning model. And the number shows how many times a substitution is used to optimize a model. And so the orange box shows substitutions that are currently missing in TensorFlow. And one really interesting observation of this heat map is that it turns out different deep learning models actually require different substitutions. So this means that our today's optimization designing for existing models will unlikely generalize to new models. And you must figure out an automated way to discover these new models instead of using human heuristics. So to conclude, I have presented TASO, which is the first deep learning optimizer that automatically generates substitutions. And TASO requires significantly less engineering effort, achieves better performance, and also provides formal verification on the correctness of our graph substitutions. And TASO has been fully open sourced. Currently, we support optimizing arbitrary DE models in ONNX, TensorFlow, and PyTorch graph formats. And feel free to use TASO to optimize your deep learning model. And with that, I would be happy to take any questions. Thank you.
Hi, Cheng Tan from NYU. So I'm wondering, like, who will guarantee the correctness of each of the operator specification? Because if you specification and the operator implementation doesn't match, there's no correctness guarantee.
Right. So the question is how to guarantee that the operator specifications are actually correct. So the operator specifications are provided by user, and we also have some automated way to check the correctness. So first, we check the correctness of the operator specifications on small tensors, because we cannot check the correctness for arbitrary large tensors. So we check the correctness on tensors with size up to 4 by 4 by 4 by 4. And we can prove that it is correct for small tensors. And we also have some redundancy check, making sure that you don't have any redundant operator properties.
Okay, thank you.
Thank you.
Paul Barham from Google. So it seems to me that the fingerprinting technique you're using is based on random inputs, and there are a lot of operators.
I'm sorry, I cannot hear your question.
The fingerprinting you're using seems to be based on random inputs to a small graph. There are a lot of operators in some of these frameworks that have quite fiddly validity constraints on the inputs, like gathers where you have to pass in valid indices. It seems like this is sort of related to fuzzing, where the correctness of the input might be.
I'm sorry, I just hear that the substitutions are generated using random inputs.
Yes.
So what's your question?
The question is that a random input might not generate anything that is reasonable or valid for a bunch of operators in these frameworks.
Okay, so we think that if a substitution is correct for arbitrary inputs, then it should also be correct for our randomized inputs. But the other way is not correct, because they are equivalent on randomized inputs doesn't mean they are equivalent on arbitrary inputs. And that's why we have the formal verification to guarantee the correctness on arbitrary inputs.
Okay.
Yeah, so maybe we can talk offline. Thank you.
Rashmi from CMU, very nice talk. So I had a quick question regarding the ability of this approach to scale. So if I understood correctly, the graph substitutions that were generated were for 4 operators, right?
Right.
And that related in 66 million possibilities.
Right.
So was that parameter 4 chosen based on certain understanding of that's a good number to optimize for? Or, and can it scale for
So the question is, can we scale beyond 4 operators to 5 and 6? So the limitation is the generator, because we have to save the fingerprint of all possible subgraphs. And saving the fingerprint on graphs with 5 operators will exceed the main memory on a single machine. Okay. So I think in the future, if we implement a distributed generator, we might be able to scale to 5 or even 6 different operators. But that will be the future work of this paper.
Okay, so basically the fundamental limitation is the memory size then?
Right, the limitation is the memory capacity on saving the fingerprints.
Okay, thank you.
Thank you.
All right, that wraps up our session.